we're going to have in line losses here, or time, number of feet. So let's say we have 10 feet. We're going to multiply that by 4 for elbows and things like that, so 40 feet. So correction for elbows, multiplier for elbows, maybe it's a better way to say that. Elbows, strainers, valves, manual valves, et cetera, et cetera, et cetera. Okay, and so .051. So our delta P 0.02 psi, which means that a more accurate version of that source pressure is 14.7 minus 0.02 psi equals 14.68 psi. My assumption was pretty close. So there's my inlet pressure to the pump, 14.68 psi, aka 14.7. What about the what, sorry? Yes, that's right. There is an elevation difference there. That's a good point, Josh. Thanks. Yep. Okay, so the delta P of the elevation. Okay, so that's rho GH. Keeping me honest, that's good. So that's 10 feet times 0.43352. That's my conversion factor. The density of water is 1, so I don't need to correct for that. So that is obviously 4.3 psi in elevation losses. So now my new inlet pressure, which is the right one, is, oops, did that wrong, 10.3. Okay, so good thing you caught that on me. Thank you. 10.38 psi. psi A. On to number 4. Which is the discharge pressure. So our destination pressure down there is 0 psig, because it's an open pond. Our line losses. Okay, so now we want to try and run a smaller line because this is costing us some serious money here. So we want to go back to our line sizing here and look for something a little bit more aggressive here. We could probably look at that velocity. That would be a 4-inch line. So, and a 4-inch line could easily go up in terms of pressure. We could probably push it up into sort of 300 gallons a minute if we needed to. So that might be a reasonable way to go. Since it is a main header into a system like this, and we might end up needing a lot of water to fill the ponds initially, that's not something I'm really considering at this point in time, but we might actually want to run maybe a 6-inch line just so that we can push up in terms of higher flow rates for filling and things like that. So maybe what we should do is be thinking about a 6-inch line here. Normally I would have just gone straight for the 4-inch line, but this is I think a special case. So we might even go back and rethink that a little bit more and try and come up with what's a reasonable filling rate for the ponds. We know roughly what the volume of the ponds is, and say we want to fill it over the course of a week or 2 weeks or something like that, a long period of time, because it's a lot of water, and then go back and recalculate what another reasonable flow rate would be for special cases. For now, I think I'll go with a 6-inch line. And my 6-inch line has 0.2 psi per 100 feet. And we have 4602 meters. 3.28. So we have about 15,000 feet. So our line losses are 15,100 feet times 0.2 psi per 100 feet. So we have about 30 psi of line losses. Now, we should put that 4 multiplier in there to cover all the elbows, all the T's, all that kind of good stuff. That might be a little excessive for this because we've got so many just straight lines without having, we're not really going to have as many elbows in there as we would normally have. So maybe what we should do is, well, for worst case, let's put it in there anyway. I think this is a good situation where you might actually go back and do this line hydraulics rigorously. So sit down with a program, put the number of elbows in, get a better design. We've got a really good design there. Elbows and valves, etc. We could easily do this a lot more accurately, because that goes up to 120 psi. My engineering intuition is telling me, this should be, actually, you know what? It's probably not far off. So we're gonna need some control valves up by the ponds here. I'd forgotten about. There's going to be level valves up on the ponds. So if I can imagine that's a pretty good pressure for the discharge pressure of the pump. I'm going to change this to a 1.5 factor. And so that's going to be about 45 psi in the lines alone. So that's what my intuition is telling me. But seriously, I would sit down and just do this rigorously. We've got a good 3D model layout. I would throw it into a pressure drop program and actually calculate this properly. That's my advice to you guys for something like this. Okay, other things we have flow elements. We have one, and so they're about 3 psi. It's probably reasonable. We're going to have control valves. So a bunch of different ways to do the control valves here. Let's see if we can pop up the okay, control valves, tools and programs. an opening. Okay, so we have 250. And we'll just go with the standard sort of D ratings on this one for now. That actually could go down a little bit there. Pump suction pressure is right around minus about 10, minus 5, roughly. Specific gravity is 1. Destination pressure is basically 0. And our static head, we said, is, what is that static head? 263. Okay, so 310 minus 263. So 47 feet of static head. Sounds about right. Frictional losses, we're saying about 45 pounds in frictional losses. I'm going to go with an 1800 RPM pump. And our control valve guess value, we'll say, is 25 pounds for now. So Connell, right off the bat, Connell's telling me I need 30 pounds across my control valve here. So we could go with that if we wanted. Let's try a couple different ways here. Control valve, 30 psi for Connell's method. I don't think it needs to be that much. Let's see here. Okay, so an estimate of the pump differential pressure at low flow and high flow, it's probably is not bad. And essentially what we need to do is goal seek the control valve pressure drop so that that ratio is 10. Let's just go up in pressure here. Just, you gotta get actually calculate a number there. Okay, so 50, 60. What's going wrong? 40 for a second here. There we go. I gotta go down. Okay, so we can just goal seek this if we want. Where's the goal seek here? You guys know how to use goal. I'm sure you guys know how to use goal seek, right? So we want to goal seek that number to 10 by changing the control valve guess value. There we go. My method says 37 psi to get the kind of control range that we're looking there. So we got a choice. We got a decision to make there. Either we want to revise our min and max flow rates, or we go with one of those pressure drops. If we went up to say, I don't know whether this is going to actually happen or not, but say 300 gallons a minute, 600 gallons a minute, or something like that, then this pressure drop guess value is probably going to have to go up, I think. It's going to have to go up a lot. Yeah. Wow. So if we really want to get that kind of flow rate, we're going to need multiple pumps, I'd say, because we don't want to put that across the control valve. Okay, so that's not what we want to do. That helps, actually. And we'll go back to, say, 37 pounds or whatever it was. Yeah, okay, so I'm going to put 37 pounds. Gee, it seems high, but anyway, I'll go with my method with 37 pounds across the control valve and see if I missed anything else. We're still good with tape, James? Okay. So flow element. Oh, we've got another level valve here that we need to account for a little bit there. So I'm going to just assume that we're going to have 10 pounds across that other control valve for level valve on the pond. I think that's it, right? We need some flow elements. We've got one flow element there. Oh yeah, we've got two flow elements, right? Okay. So that's going to be 6 at 3 psi per. Actually, you know what? I'm just thinking about this. The flow rate in this section of the line here is actually a lot higher than this flow rate. So in reality, what we should be doing is we should actually stop and redo the calculations from this point forwards. Like we're going to have a different line size for that. And it will probably have a slightly different pressure drop per 100 feet. Everything else will be basically the same. The elevation losses are the same and all that good stuff. Maybe we'll rip through this way for now, and then we can go back and just check to see how much difference that would be when we added the flow rate in and resized that line. So the frictional losses may not change too much in the line, so it may not affect our pump size too much. But definitely there's a much bigger line size that needs to run around the ponds. Okay, so let's just add that all up. So we have 45 there, another 6 here, 37 here, and another 10 there. So we have 98 PSIG on the discharge of the pump. We're actually getting really close to be done. Okay, so we got the discharge pressure. Now we need the shaft power here. Because I'm running out of space. Okay, so the hydraulic horsepower is equal to the flow rate in GPM, 249, times the delta P, which is 98 PSIG minus, and this is minus 4.3 PSIG minus 4.3 PSI, 3.2 PSIG, all over 1714. That's the conversion factor. So 98, add that, 249, 1714. And it comes out at being actually really small. Wow, that's really surprising. It's only 15 horsepower, hydraulic horsepower. Let's say the efficiency is, say 50%. So the brake horsepower, or shaft horsepower, is equal to 15 horsepower divided by 50%. Giving me about 30 horsepower, and that's actually not a very big pump. Did I do that right? 249, 103 roughly, 1714. Yep. That's all you really need in order to get a pump. Now you can go shopping for the pump if you want. And where is that here? Oh, let's hope it remembers my password because I can't remember what it is. Let's hope this works. Not sure whether it will or not. going to need a password, and I can't remember what my password is now. Maybe. Give it a minute, chug away there. Okay, so while it's chugging away there, the NPSH calculations for this one are relatively quick. What we need is the vapor pressure of the water. We need to take a worst case scenario. Like obviously the lake water temperature is changing throughout the year. We need a worst case scenario. So possibly if they drew it from deep enough, the temperature wouldn't change too much. But I think you probably want to count on something like 15 degrees as a worst case. Water. You know what, this actually might work better in Internet Explorer for me. Okay, so we need the vapor pressure of 15 degrees C water. We can do that really quickly with HYSYS, because that doesn't seem like it's working very well for me, does it? Whoa, what happened there? Okay, so if you want the vapor pressure of a stream, let's just pop up HYSYS and do it real quick. I just need a stream. I just need to tell that it's water. Whoops, that's not right. Ah. Okay, there we go. And we want it at 15 degrees. And we want to just set it right at its dew point. And there's the vapor pressure right there, 1.7, otherwise known as 0.247 psia. Okay, so I'll do it right here, so it's on the same board. NPSH available. Still okay for tape? 10 minutes? Okay, cool. Okay, so what I need is the difference between the vapor pressure and the actual pressure at the pump. So my actual pressure is 10.38. Minus the vapor pressure, which is 0.247 psia. Okay, because I've accounted for all my line losses and stuff like that in here already. So that makes that fairly simple. And the difference is 10 point, whatever it is. So 10.1 psia, and then we just basically convert that into feet with rho GH. So I just take 0.43352 divided by that, so 10.13 divided by 0.43352, and the specific gravity, which is 1, and we get 23.37 feet of liquid. So we're looking for a pump that requires less than 23.4 feet of NPSH. And actually what we probably want to do is put a 1.2 multiplier on there, because we want either minimum of 3 feet or 20%. So that's available So the pump we picked should have an NPSH required of 28 feet or more. You should say greater than 28 feet. It's a better way to do it. And let's see if this ever popped up for us or not. It doesn't look like it actually happened for it. Just did it. I find sometimes Internet Explorer is actually better for this. Let's try Internet Explorer and see if we can get it to work. If not, we'll do it on the VDI because I think the VDI. Let's see if that works. Should pop up with a little dialog box here with your password requirements. Takes a minute sometimes. Questions? Yeah, Jeff.
For the line losses, what do we use if we're not using water? Like this one was the grain manual, but for all the other ones, do we just assume that it has the same losses as water would?
You got to make a judgment call. You can either do that, or you can pop up HYSYS and put a pipe segment in and do the pressure drop calculations in HYSYS. So that's not terribly hard to do. Whoops. Where is that pipe segment now? Lost it in the new version. There it is. So you can do that. And then you can actually try different viscosities if you want. Because you're able to, I haven't done this in ages, you guys. I forget how to do this. I got to go look at it. There it is. That's what we're trying to do. So you add a segment, append a segment there, and then basically you can put your elevations in, and somewhere in here is a way to put fittings in. Yeah, you can get fairly complicated with this, but all you really need is put 100 feet of pipe in there, and put your fluid in, and calculate the pressure drop per 100 feet of piping, and then you can use these rules of thumb. So that's a quick way to do it. Yep. Okay. I think we're pretty much done anyway, except for the pump sizing selector. Yeah. Oh, okay. We got 4 minutes. We'll just let it run. Yeah. Any other questions? So what you can do is just look at your viscosity and see if your viscosity is roughly close to water, and then you can decide whether you want to use the crane tables or not. Yeah. Any other good questions? Is that helpful at all, or? Yeah, a little bit. Okay. I was thinking of kind of doing the reactor one as well, but it's pretty straightforward. Oh, the only thing I was going to kind of maybe make it as an extension, we can do it after the tape runs out, is maybe have a look at what this would happen once we bring the raceway return in, because that's going to be the majority of the water flowing around is that raceway return for sure. How I would handle that. So very simply, I would just put an expand the pipe right here, and look at the combined flow rate that's needed there, and just check my frictional losses through there. I'm pretty sure the frictional losses won't change very much from there, because you as the process engineers have the ability to just change the diameter, so you can almost almost pick whatever frictional losses you want because you get to pick the pipe diameter. I'll try and get the pump sizing selector working as well. Not sure why that's not working on my computer, but I guess it's not surprising on mine. Any other questions before we wrap it up? Okay, well, that's it.